Alrighty, so we're going to try something new for this lesson. They keep telling me you need to do PowerPoints because of this whole online teaching thing, so I caved in. I did a PowerPoint for this section. We'll see how well it goes and whether or not I like it, or I'm just going to go back to my own thing because, I think doing my own thing is better, but what do I know? I'm just a teacher. So, 9.2 will all be about this thing called the dot product. And why are we going to talk about this thing called a dot product? So far, last week in 9.1, we talked about arithmetic operations of vectors. When we have two vectors in component form, it's very easy to add and subtract them. As you can see here, I went ahead and wrote the vectors in a stacked column notation because I think it looks a bit more professional, neater. But if you don't like it in your notes, you can always um, write it in angle bracket notation, whatever notation you like. Also, another thing I forgot to mention, since it is PowerPoints, I'm obviously going to go a lot faster because it's less writing for me. If at any time I'm going way too fast, since this is a video, you can always just pause it, jot things down in your notes, and then continue the video. So again, if you don't like the stacked column notation, you can just go ahead and rewrite it in the angle bracket notation. So vector v is vx, vy. So therefore, u plus v is ux plus vx, comma, uy plus vy. And the same thing for subtraction, except of course, you subtract. U sub x minus v sub x, comma, u sub y minus v sub y. And we didn't really talk about multiplication per se, but we did talk about scalar multiplication. So if you take one vector, that's the key there, one vector and any non-zero number, then if you were to multiply that vector by that number, it's just the distributive property. You multiply each separate piece by that non-zero number. But of course, it stands to reason, if we can add vectors and if we can subtract vectors, what about multiplying two vectors? Well, remember that when it comes to vectors, which are physical geometric objects, there needs to be a physical meaning behind them. For instance, there is a physical meaning for addition. Remember, we started with adding vectors graphically using this tail to tip method. If you wanted to add two vectors, you just draw the second vector where the first vector ends. So for instance, if I want to add this u and v, I could draw vector v, where vector u ends, and then wherever my original starting point was, all the way to the final point, terminal point, is the sum. And we saw that with this, the standard properties of real numbers apply to vectors, and that vector addition is commutative. So instead of starting with vector u, I could have started with vector v, tacked on vector u, and you get the same sum. So that's why vector addition is sometimes called like parallelogram addition, because it creates a parallelogram. So we can visually see, well, visually see, that's redundant. We can see graphically what the meaning of adding and subtracting is. The question is, what does multiplying vectors mean graphically? Now, we got to be careful about multiplying vectors because unlike real numbers, where multiplication is just multiplication, there are various ways to think about multiplying vectors. There are these two ways you can multiply vectors. One is called the scalar product and the other is called the vector product. We'll talk about the scalar product today. We'll save the vector product tomorrow. This thing called a dot product is called a scalar product because the answer that we get will always be a number. So this is a pretty weird thing with vectors. Like, let's go back to adding and subtracting. What do you get when you add two vectors? You get another vector, right? A vector plus a vector is a vector. This dot product thing, however, when you do this dot product with two vectors, you actually get a scalar or a regular number out. So it's a pretty different concept. A vector dot another vector is a regular number, not a vector. Well, it turns out that the logic behind the dot product is the same logic we use when we multiply regular numbers. Now, I know there are a lot of things that you were taught in elementary school when it came to multiplying. The very common one is multiplying is repeated addition, and certainly there is some merit to that. But I want you guys to think of multiplying numbers in a different way. Recall that we organize numbers on the number line, and numbers can be thought of as lengths. So, for example, here 2 times 4. You can sort of think of 2 as this length here. That's sort of the idea of 2-ness. 2 is this length right here. And when I do something like 2 times 4, what you're really doing is elongating, or you're stretching by a particular factor. In this case, 2 times 4 says take the idea of 2-ness and stretch it out so it's 4 times as long. And we all know just by arithmetic that 2 times 4 is 8. So that's sort of what happens. You can see that this 8 is this idea of 2-ness, right? But you have 4 times as long. So this is the idea of 2-ness, and this is 4 2's. So that I want you guys to understand what it means to multiply. Is you're stretching a number in one direction. I think I wrote that down there. Okay, yeah. So you can think of regular multiplication as directional stretching. And I put the word directional there is because, eventually we learn about multiplying by negatives. And the same logic can be done with negatives as well. So if we take the same example, but with negative, 2 times negative 4, all this negative means is you stretch in the opposite direction. So the job of a negative when you multiply is to turn around. So when I do 2 times negative 4, I want to stretch the idea of 2-ness. I want to stretch this idea of 2-ness, but not pointing towards the right, pointing towards the left because I'm multiplying by negative 4. So here is multiplying by negative. So this is going to be 2 times negative 1. So we're at negative 2. And then we stretch it out 4 times. So that's sort of the idea of multiplying by a negative. So idea of multiplying is just directional stretching. Multiply by a positive, you're in the same direction. Multiply by a negative, you're stretching in the opposite direction. Now, this is easy for us to learn in, elementary school, middle school, because up until, algebra 2, we've only been working with one-dimensional numbers. That's what the real number system is. It's just one dimension. You're only living on this real number line here. Of course, we know vectors is a two-dimensional number, right? It could be angled. So what we need to do is sort of translate or apply this one-directional knowledge of multiplying in both directions. How can we do that? Well, we need to have vectors be algebra friendly. In the 3 notations of vectors, these 2 here, the stacked column notation and the angle bracket notation, is great. It looks sleek, it looks clean, but it's still an abstract symbol. The I and J notation, where I and J are the unit horizontal and unit vertical vectors, at least becomes algebraic terms because of this plus sign here, so you can use regular math on them. And that's what I want to do first here. So in order to apply this idea of regular multiplication to vectors, we're going to first think of vectors as algebraic terms, as actual numbers, using this I and J notation. So let's go ahead and do that, right? So let's go ahead and multiply 2 vectors in this I and J notation, because again, if it's in this I and J notation, we can exploit regular multiplication knowledge. So if we have 2 vectors, let's say x sub 1 is the horizontal of the u, and y sub 1 is the horizontal of v, and x sub 2 is the vertical of the vertical of the u. If x sub 2 is the horizontal of the v, and y sub 2 is the vertical of the v, then what I want to consider is multiplying them. So what is u dot v? And that's exactly how we pronounce it. We wouldn't say u times v, we would pronounce it as u dot v. Well, just do straight up substitution. You have this guy here times that guy there. And notice what we have. This is just a regular multiplying 2 binomials. We should know how to multiply 2 binomials by now. It's just repeated distribution. I guess if you want to go old school, back to pre-algebra, your teacher probably taught it to you as FOIL, but it really is repeated distribution. So let's go ahead and do that. So first we're going to distribute the x sub 1i. So x sub 1i times x sub 2i there you go, plus x sub 1I times y sub 2j plus y sub 1j times x sub 2I plus y sub 1j times y sub 2j. Right? So although this looks crazy complicated, it looks scarier than it really is. All it is just doing regular multiplication with two vectors in I and j notation. Well, let's really graphically understand what this means, right? So that's the question. What does all this gibberish really means? And I think I can best explain it when we look at it graphically. Well, remember that the I denotes horizontal direction and the J denotes vertical direction. So this expression here literally says, take this quantity, which is the horizontal of x sub 1, and we're going to scale it x sub 2 times in the horizontal direction. So we're going to stretch the number x sub 1, whatever that is, by the number x sub 2 in the horizontal direction. And the same, and you can repeat the idea below. This next term here means take this number, the x sub 1 horizontal, and we're going to stretch it y sub 2 times in the vertical direction, in the j direction. This means take the y sub 1 in the vertical, stretch it by x sub 2 horizontal. This means take the y sub 1 vertical and stretch it to the y sub 2 vertical. Now, in this giant expression, which again is the dot product, there's a formula for the dot product. There are a couple of terms that are sort of weird, and we can sort of see it if I translate all of these weird symbols into actual geometric lengths. So again, I'm going to do the dot product. I'm going to express this dot product formula with shapes. Remember that the i's are the horizontal components, and the j's are the vertical components. The sub 1's came from the u's, and the sub 2's came from the v's. So this right here, x sub 1I times x sub 2I says I'm going to take the horizontal of the u vector, which looks like this, and I'm going to times them by the horizontal of the v vector, which looks like that. Then we have plus, and then we got this guy here, which is the horizontal of the u vector, x sub 1, times, and we have the vertical vector, because it's the j, of the second vector, which is v, so the vertical of the v. Plus, we have what? The vertical of the u vector times the, what is that? That's the horizontal of the v vector. Plus, and last but not least, we have the vertical of the u vector times the vertical of the v vector. Now, if we employ the idea that multiplying is just directional stretching, then these two inner multiplications should not make sense to us. Because why? Let's take a look at this guy here. This says take a horizontal length, and I want to stretch it vertically. So imagine you had, what's a good analogy? Imagine you had clay, a rubber band. Oh no, that stretches in all directions. Okay, I don't have a really good analogy for this. Well, actually, a slinky. Imagine we had a slinky, right? And you had a horizontal slinky, and you don't want to break the slinky. So obviously I can tug this slinky and distort it, but then it would ruin it. So if you had a horizontal slinky, you can only open it left to right horizontally. Well, what this guy says here is I want you to take this horizontal slinky and stretch it up without breaking the slinky. That is impossible, right? Because a horizontal slinky can only go left to right. So what answer should I get if I have, here's the horizontal number, now stretch it vertically? Well, I hope it makes sense to everyone that your answer should be 0, because if you have a horizontal slinky, there's nothing in the vertical direction. So nothing vertical times vertical, anything times nothing should be 0. And of course, we can apply the same logic to the second quantity. Take a vertical slinky. So you have a slinky that's standing straight up. I want you to, what this says is, I want you to stretch it horizontally without breaking or distorting the slinky. That is impossible. They are not in the same direction, so direction multiplication won't work. That's also going to be 0. So that means in our wickedly crazy dot product formula, those middle terms, they all end up to be 0. So we're left with this nicer, cleaner, and I think a conceptually no duh, it makes sense formula, which we call the dot product, right? So the dot product is something that you are going to use a lot in the future in your calculus classes or in your physics classes, or if you plan on going to engineering. But here's the formal definition. You can go ahead and pause the video and to give you guys more time to copy it down. But if you have two vectors in component form, that's the key there. It needs to be in component form. Then the dot product is simply the sum of the products of their components. In other words, the dot product is just taking horizontal times horizontal and adding it to vertical times vertical. So it's going to take a while to understand conceptually what the dot product is, but in terms of skills, in terms of actually using it, it's a piece of cake. It's like sixth grade math. If you can multiply and add, you can use dot product. So let's do these two examples really quickly here. So letter A, what is u dot v? Because it says find the dot product. Well, u dot v, I'll go ahead and show my work. Now remember, a dot product is a scalar product, so the final answer should be a regular number, not a vector. So do not write it in vector notation. It's going to be x times x plus y times y. And of course, to show my work, that's going to be 2. Now, what does that mean? Right now, it's not going to mean much when we take dot products without doing a word problem or an application problem. You're just figuring out a random number. So bear with me, it's going to be a random number for now, but let's go back to the regular idea of multiplication. Remember how I was sort of harping on multiplication as directed stretching? So because we got a positive number 2, this says, all things, if you were to fudge the numbers, if you were to squint your eyes, these vectors are not in the same direction, but because it's a positive number, it's, at least somewhat pointing in the same direction. So the dot product is sort of like a quantity that describes how much the numbers are, how much the vectors are pointing in the same direction, and whatever parts that are pointing in the same direction, you scale it like regular multiplication. But let's do letter B really quickly. I only put letter B here because, hey, it's an I and J notation. It really doesn't change the concept when it's in a different notation. So u dot v is still the x component times the x component plus the y component times the y component, right? So in PowerPoint, man, the pen writes ugly. So it's going to be 10 plus a negative 6, which is a 4. So since this was a bigger number, I can say that the magnitudes of this of the pairs of vectors in B point more in the same direction than vectors listed in A. Now, because the dot product is like analogous to multiplying of regular numbers, not surprisingly that some properties transfer over from the real number system to the vector system. So dot product is commutative, as we expect. 5 times 2 is 2 times 5, same thing with vectors. It is associative, as we expect. It is distributive, as we expect. And this last one's just a pretty neat fact. When you take the dot product of a vector by itself, it is equivalent to squaring the magnitude. And that should make sense, because a dot product measures how parallel, how much two vectors are pointing in the same direction. So if you're doing the dot product with itself, of course they're going to be in the same direction. So you're basically doing all of the vector times all of the vector, which means, magnitude times magnitude is magnitude squared. So although this is a pretty neat property, and we can sort of prove it algebraically, I don't want to just believe it based upon the proof. I want you to really understand it. A dot product is like regular multiplication. It's scaling. So if we dot a vector by itself, of course they're going to be 100% in the same direction. So you scale their magnitudes, and magnitude times magnitude is, of course, magnitude squared. So that's a pretty obvious, but not so obvious at the same time. It's a weird thing. It's obvious when you understand it. Math is easy once you understand it. But when you really truly understand what vectors mean and what the dot product means, that's just a wow conclusion, wow result. Now, we developed this idea of the dot product and we came up with an algebraic formula, right? We came up with this formula by doing regular repeated distribution. We took the I and J notation and just FOILed it. I want to do the same thing. I want to come up with a formula for the dot product, but I want to take a different line of thinking. And you're probably going, why are we doing this? Well, by doing a different line of thinking, we actually come up with a pretty cool different result. So we got the original form for the dot product by taking the components of these two vectors and foiling, right? Repeated distribution. I want to take the same picture and rotate it. And this is legal to do because hopefully we remember from geometry that if we apply a rigid body transformation, which rotation is, then all of the quantities of the figure are preserved. The angles are preserved, the angles are preserved, I said that twice. The angles are preserved, the lengths are preserved, the area, the shape, the smell, the size, its likes and dislikes, it's all 100% the same. So it should, I hope you guys can convince yourself it's completely legal to rotate this figure here. I just want to rotate it so one of the vectors is flat, and then we're going to go ahead and do the whole dot product with all the components. But the key interesting thing here is, so if I call this length u, vector u, so that length is the magnitude of u, and if this is vector v, this becomes the length, the magnitude of v. The interesting thing is when you rotate it, vector v no longer has a vertical component. By rotating so that one of the vectors, without loss of generality, let's call it v, is purely flat, that means it does not have a vertical component, which means the horizontal component of vector v is the entire magnitude. So when we do the dot product, because there is no vertical component of v, I can just ignore that part of the dot product. Remember the dot product u dot v was horizontal times horizontal plus vertical times vertical. Well, if one of the components doesn't have a vertical, that's 0, we can just basically ignore that, and it just becomes the product of the horizontal components. So that's what that sentence means. But, and as I've already said, if I rotate so that one of the vectors is purely horizontal, then the horizontal component of one of the vectors, which I've labeled as v, is the entire magnitude. But because vector u is still at an angle, the horizontal component of vector u is that horizontal component formula, magnitude times cosine of theta, where theta in this case is the angle between them. So again, this theta here is the same as this theta here. So normally it's the direction of the vector, but in this case theta is playing the role as the angle between the two vectors. So what is the dot product? The dot product is this guy here. It's the product of the horizontal components. I just went ahead and put the magnitudes in front. Now this is also a valid formula, and you can go ahead and box it in your notes if you want. It's just that most mathematicians, most math textbooks, they don't print it out in this version. What they do is they isolate the cosine, so they go ahead and divide out the magnitudes. You don't have to copy it down right here. It's on the next slide. But this is typically what we do from this point on. So we get the alternative definition that involves the dot product, which becomes the angle between two vectors formula. This formula here will actually give you the angle between any two vectors without needing to rotate one of them. So if I were to draw two random vectors, I don't need one of them to be horizontal or vertical. With this formula, we can find the angle between these two vectors, right? So let's go ahead and just do it, right? Let's do these two examples. So find the angle between these two vectors here, and normally what this would entail is you'd take out some graph paper. So back in the day, you would take out some graph paper, draw the vectors, break out a protractor. Here we have math to help us. So we're just going to apply the formula. So it's going to be the dot product. So x times x plus y times y all over the magnitudes of each. So the magnitude of u is x squared plus y squared. times the magnitude of v is x squared plus y squared. And it just dawned to me that I don't even have a calculator out here. So there's going to be like a 30-second to 1-minute pause in this video. So feel free to fast forward. Sorry about that. That's what you get for not being a video editor and making all these videos in one take. So, hopefully you guys can see here, in order to solve it, you just take the inverse cosine, right? Let's go ahead and do degrees. Typically, when I find angle between two vectors, I always stay in degrees because almost always it will not be perfect. So let's see, cosine inverse of 8 minus 15, so what's that in that? Negative 7, divided by the square root of, what's that, 4 and 25, so that's 29, times the square root of 9 plus 16. Oh, that's easy, 25, so 5. So, oh, I'm in radian mode. Jeez, I say I always do in degrees, and I didn't put it in the right mode. So in degrees, I get 105.1 degrees. So theta is about 105.1 degrees. So without drawing these out, and of course you could draw it out, right? So vector u is 2, 5, something like that. And vector v is 4, negative 3, something like that. Without breaking out a protractor, you can bet money that this angle here is about 105.1 degrees. Now, remember how before I always say, caution, caution, whenever you use inverse trig functions. When it comes to using this formula, you don't have to worry. Why is that? Well, by standard convention, we always take the smaller angle when defining the angle between two vectors. What do I mean by that? Well, if you just draw two random vectors, you notice how you always create two angles. You always create the smaller angle and the bigger angle here. That's just nature. That's just natural. When you make a V shape, you're always making two angles. And by standard convention, we always define the angle between two vectors, a smaller one. So what are the ranges? Like, what are the possible outputs of angles between two vectors? Well, in the extreme cases, you can have two vectors that are lying on top of each other, right? Here's one. Why won't that go away? Eraser. Let me see if I go back and forth. It's still showing up on my screen. There we go. You could have the extreme case, two vectors on top of each other, which of course means that the angle between them, if they're going the same direction, is 0. Or, you can constantly rotate above it, which means the angle is going to increase 0 degrees, 1 degree, 2 degrees, 4 degrees, so on and so forth, until the other extreme case, which is the exact opposite direction, 180 degrees. Realize that beyond that point, if you get bigger than 180 degrees, we don't start going above it, 181, 182, 183. We don't do that because eventually this outer angle becomes the bigger angle. So when we define that when we define the angle between two vectors, we're going to start using the smaller angle. So you can see here that the angle between two vectors will always be within, I'll go ahead and use degrees, 0 to 180 degrees. Well, why does that, okay, whoop-de-doo, great. Why does that mean we don't have to be concerned when we take the inverse cosine? Well, recall that this is precisely the range of the inverse cosine function, right? So that means when you find the angle between two vectors using this formula, you can trust your calculator. Whatever answer your calculator gives you, boom, that is it. You don't have to deal with reference angles. You don't have to deal with quadrants because it doesn't make sense to do quadrants. We're not talking about direction. We're talking about amounts between two vectors. So as long as your numbers are correct, as long as your application of the forms are correct, whatever answer your calculator gives you for angle between two vectors, you can pretty much agree with that. You can trust it. Now, this is just only one very tiny application of dot products, and eventually throughout the whole unit we'll talk about more applications. But for this section, 9.2a, we're only going to do baby steps. What is one thing you can do with dot products? Well, you can test. It basically creates a test to see whether or not vectors are perpendicular. And it seems like a random, gee, why would I care? But if you do study calculus, physics, and engineering, it turns out that it's super duper important to know when things are perpendicular to each other. So it's always nice to have an easy test. Well, with the previous formula, the cosine theta equals dot product divided by the magnitudes, with that previous formula, we now have a test to see whether or not two vectors or lines in general, line segments, are orthogonal or perpendicular. How do we know that? Well, let's take a look at this bullet point list. Recall that the definition of two objects being perpendicular is that the angle between them is 90 degrees. We have a formula that's based upon cosine. So the cosine of 90-degree angles is, of course, 0. Well, if this is true then, right, if this is the formula that we developed, then if 0 equals him, well, we should know that the only time a fraction equals 0 is if the numerator equals 0. So that implies that the dot product equals 0. So that roundabout way, that's why we came up with the alternative definition, justifies that if you do a dot product and the answer is 0, then that means that the two vectors must be perpendicular. And again, this is like so cool. Everything goes together. The basic understanding, the basic concept of the dot product is a measurement of how much two vectors are in the same direction. If the answer is 0, that means that's the most not in the same direction you can be. And what do we call that? What is the situation when you have two vectors are just completely not remotely close going in the same direction? Is if they are not in the same dimension. One being horizontal, one being vertical, i.e. they are orthogonal. So here's a algebraic proof for it, and we have the conceptual intuition behind it. Really, really cool. Sorry to be a buzzkill though. I mean, its application is pretty simple. Just do the dot product. If it equals 0, they're perpendicular. If they're not 0, then they're not perpendicular. So let's do this really quickly. Letter A. So if I did u dot v, again, that's x times x plus y times y. We get negative 40 and 6, so it's negative 34. So not orthogonal. Easy peasy. Because it does not equal 0. Oh, gee, I can probably guess what letter B is going to show. So u dot v is x times x plus y times y. Gee whiz, that's 0. So they are, oops, not u times v. U and v are orthogonal. Okay, so easy peasy application of the dot product. Now another easy application of the dot product is to find this thing called a component. Now what is a component? Specifically, this is how you pronounce it. Component of, for example, u along v. U and v are completely arbitrary. You can swap the positions, but typically, what is the component of one vector, the first vector, along another vector, the second vector, right? You can sort of think component as the magnitude or length of, in this case, vector u that is cast upon vector v. So this diagram sort of showcases it. So if you have two vectors, and notice I didn't make it horizontal, so it's just two random vectors. If I want to do u onto v, you imagine there's a sun. Oh, well, I can't draw sun. Well, I was drawing the human, not the celestial body. If you imagine the sun right at the terminal point of u, it would cast a shadow along v. Excuse me. That length of the shadow is what we call the component, right? Well, notice it's just the horizontal component, right? It's the component of u along to v is just the horizontal component formula. Because how would I calculate this length here? G, it's the hypotenuse times the cosine of the angle. So it seems at first blush that the component of u along v is pretty simple. Take the magnitude of u and multiply it by the cosine of the angle between the two vectors. Right. Well, so that's exactly what this says. Now I boxed it in the notes, but that would not be my formal formula. It's still important, so that's why I boxed it, but you will almost always never use that. Why would you almost always never use that? Is because often you do not know the angle between two vectors. It's very rare when you spot a vector out in the wild. A wild vector appears. You wouldn't know what the angle between them is without breaking a protractor. Almost always, it's easier to find the components of the vectors than the angle between them. So, oh, by the way, this is the notation: component of u onto v. So you sort of read it zigzag: component of u onto v. So while this is a valid formula, can we come up with a formula that doesn't involve the angle between two vectors? Because that's almost always not known. Well, we can. To answer that question, yes, because we have this formula, don't we? So with these two things here combined, we can come up with a formula for the component that is completely dependent on only the vectors themselves. So it's just a straight up algebraic substitution. If this is true, which we know it is, and this is true, which we know it is, then we can take this whole guy and substitute it in for the cosine, right? And that gives us this guy here. And of course, algebra, the magnitude of u's will cancel, and then that gives us this box formula here. So this is something you could put in your index card. You can memorize it, but you know me, I always try to understand things rather than memorize it, because if you understand it, you don't need to memorize it. So the way I understand this, not memorize it, is I know that dot product is like regular multiplication. It is the parts of u and v that are in the same direction, right? It's this part here, this length here, with this length here. These are the only two parts that are in the same direction, and then you multiply it regularly. So when you do u dot v, here's u, here's v. When you do u dot v, you're getting this super duper length. Why is it super duper length? Because it's the component of u that's been elongated or stretched by the magnitude of v. So if I want to go back to the original component of u, I have to unscale it by the magnitude of v. So that's why the magnitude of v is in the denominator. So again, this is one of the cool things about vectors is, yeah, the algebra proof behind it are super duper easy, but so is the conceptual understanding. And no one's I'm not, I mean, it'd be great if you had this conceptual understanding right now, but no one wakes up in the morning, listens to one video and go, wow, I understand it all. But really spend some time on it. Spend 5 minutes just really trying to understand this conceptually, and if you do 5 to 10 minutes, I promise you wouldn't have to memorize it, because hey, it makes sense. But worst case scenario, if you don't understand it conceptually, you have an index card, it's very easy to use. It's just plug and chug, right? So what is something that you might see in a quiz or a test? Oh, here's these two vectors. Find the component of u along v. So again, if you don't know it conceptually, it's just a application Why is this messing up? You can see why I don't like PowerPoint, because the pen screws up. Let me refresh the screen. There we go. The component of u along v is the dot product of the two divided by the magnitude of the second vector, which is v. So the dot product is x times x, 1 times negative 2, plus y times y, 4 times 1, all over the magnitude of v. So it's the x of v squared plus the y v squared. So what is that? That's negative 2 plus 4 is 2 over root 5. So there you go. So that's how much, that's the length of v that comes from vector u. Now, I didn't actually look at the textbook. I just made up some random numbers. I don't know what if they rationalize or not, so just know that this is the component, but if they rationalize it, it'll look something like this. So I don't know which version the textbook uses. You're just going to have to guess, or not guess, but check your answers. So that's it. That is 9.2a. Can you do the dot product? Can you find the angle between two vectors, and can you find the component of one vector along another vector? Pretty simple formulaically. So if you want to just be a mindless robot, it's a very simple lesson, but I want you to try to understand these conceptually, because once you do, man, the world of vectors just opens up and becomes a bajillion times easier. So good luck, and I got to figure out a way to exit this. Yeah, that's the end. Discard it.